Today I'm going to teach you about what's called the mean value theorem for derivatives, okay? There's also a mean value theorem for integrals, but that's next semester, okay? This is a mean value theorem for derivatives, and basically what it says is that if f of x is continuous on a to b, and I'm going to say this graph right here is the graph of f of x. So let's call this left endpoint A and the right endpoint B. Okay, so this is A, and going straight down, the x coordinate here would be B, okay? And it's differentiable on A to B, the open. So it's not, it doesn't have to be differentiable at the endpoints. That's the point of this, okay? So it has to be continuous on the closed, differentiable on the open. This is gonna be true for a lot of theorems we cover, okay? Then there is at least one C in AB. So this point C has to be in this interval A to B, but not at the endpoints, at which the derivative at C is equal to f of B minus f of A over B minus A. So if I connect these 2 points right here, okay, so I'm going to connect them with a ruler so it's nice and straight, okay, this is saying that the slope of this line, okay, and the slope would be, and I should say this point right here would be B comma f of B, and this point right here would be A comma f of A. All right, and if I find the slope of this line, that would be m, and we could calculate that'd be f of B minus f of A over B minus A. That's this part of it, right? So what this is saying is that there's a C, and where is this C? Well, it's somewhere in between. We don't know exactly where, but it's somewhere in between, at which the slope of the tangent line, okay, so tangent line, so crossing at one point, is the same as this slope. So we're talking about parallel lines then, okay? So if I draw this, I could kind of guesstimate kind of where it's at, okay? If I try to line these up and make this and this one parallel, okay, so right about here, okay, so I'm trying to draw it so that this one, maybe it's off a little bit, okay, but pretty close. So right about here is where it's happening. So that would be my C. Now I'm guessing it, but I can actually figure out where this is located, okay, using a little bit of math. So this slope right here, okay, is, since it's the tangent line, m is equal to f prime of C. So these two have to be the same, okay? All right, so this says the tangent slope at x equals C is equal to, and this is called the secant slope. Remember, secant is a slope between 2 points, okay? So secant slope between x equals A and x equals B. Okay, this is also saying the instantaneous rate of change at x equals C has to equal the average rate of change between x equals A and x equals B. Okay, so the slope between 2 points, if it has to meet these conditions, it has to be continuous on the closed interval and differentiable on the open interval. And I just realized you couldn't see any of that. Okay, instantaneous rate of change. You guys aren't there to say, hey, Mr. Mitchell, I can't see it. Instantaneous rate of change at x equals C is equal to the average rate of change between x equals A and x equals B. So if you need to, pause it so you can copy this down, okay? Basically, and I know I didn't do a very good job, okay? These two lines are parallel, okay, which means parallel lines have the same slope. So the slopes are the same, okay? So there has to be a derivative that has the same exact value as the slope between the two endpoints, basically, okay? And this, where it's going to occur is in between A and B. So it can't be at A and it can't be at B. All right? This next one is a special case of the mean value theorem, okay? And it's called the Rolle's theorem, all right? And basically it's the same thing, okay? But it's going to tell you that the slope is 0. And here's why. If these two are the same value, if this, let's call this A, okay? So this would be A, and this would be B. And if f of A and f of B are the same value, we'd have a horizontal line that would go through those, right? And what do we know about horizontal lines? Horizontal lines have a slope of 0. Okay, so if the endpoints are at the same level, or if they have the same value, okay, then that's telling us that there has to be a derivative that's also 0. And in this case, it's happening right here. Okay, and once again, the two lines are parallel, right? Okay, but this is only going to happen when the two endpoints are equal to each other. Okay, so this again is M is equal to F prime of C. And this is a special case where M is equal to F of B minus F of A over B minus A. And because F of A and F of B are the same, then that comes out to be 0 because the numerator would be 0 here. Okay? So there has to be at least one. Now there might be more, okay, because this could come up and down, right? Okay, so, but there's at least one of them in which this would happen, okay? Okay, so for the next 4 examples, we want to state whether the function satisfies the hypothesis of the mean value theorem. That's the if part, okay, on the given interval. And if it does, find each c in the interval that satisfies this. So we're going to actually find the c value where this occurs, okay? So we know that this is a cubic, and what do we know about a cubic? A cubic is continuous and it's also differentiable. Okay, so this is a polynomial. You could also say this is a polynomial function, and polynomial functions are continuous everywhere and also differentiable anywhere. Okay, so there's no corners, no cusps, no discontinuities. Okay, so because this is a polynomial, we know that f of x is continuous on the closed interval, and we need to state this because we need this to be able to say what we're going to say next, okay? And it needs to be differentiable on the open interval -1 to 1, okay? And so by the MVT, and MVT stands for mean value theorem, there must be a C, or at least you could also say at least one C, at least a, I wrote C, A twice. Hold on. There's not an AA, okay? There must be a, what's wrong with my whiteout? There must be a C in the open interval -1 to 1 such that f prime of C is equal to f of 1 minus f of -1, because those are my endpoints, over 1 minus -1, okay? So, okay, a few things we need to do, okay, is f of 1 would be 1 minus 1 minus 2, so that'd be -2, okay? And I also need to find f prime of C. So f prime of x, and x represents any point, C represents the specific point that we're finding, okay? So f prime of x is equal to 3x squared minus 2x minus 2. So that means f prime of c would equal 3c squared minus 2c minus 2, okay? So that would mean 3c squared minus 2c minus 2 must equal f of 1, and f of 1 is negative 2, minus f of negative 1, so that'd be negative 1 minus 1, which is negative 2, okay, plus 2, so that'd be 0, so minus 0 over 1 plus 1, which would be 2. Okay, so negative 2 minus 0 is negative 2 over 2. That'd be 3c squared minus 2c minus 2 is equal to negative 1. Okay, so now we need to solve this, okay? And then when we solve this, the c value that we get has to be in between negative 1 and 1, but not be at the endpoints, okay? So here we go. Okay, so since it's a quadratic, I'm going to move this 1 over here over to the other side. And so we get 3c squared minus 2c, and then I'm adding 1, so that makes that minus 1 is equal to 0. Okay, so I'm going to try to factor this, and so we're looking for a product that is equal to 3 times negative 1, which would be equal to negative 3, and we need the sum to be equal to negative 2, and that's, we can find two numbers that do that, right? It'd be negative 3 and positive 1. So we can make our area model. We haven't done this in a while, huh? Okay, so this would be 3c squared, and then these two would be negative 3c and positive 1c. Wouldn't matter where you put which one, okay? And then this would be negative 1 right here, okay? So GCF across the top would be 3c, and GCF here would be just c, and this would be plus 1, and this would be minus 1, okay? So that means this factors into 3c plus 1 times c minus 1 equals 0, which means c would have to equal negative 1/3, or over here, c would equal 1, okay? But, okay, this isn't one of them because that is actually on the endpoint. And we're saying here, this theorem says it has to be in between, okay? So, all right, c equals 1 is not a solution. Okay, because 1 is not in the interval, open interval, negative 1 to 1, okay? So our only answer is c is equal to, and let me slide this up a little bit, c is equal to negative 1/3, and that's our only answer, okay? So this slope, okay, the slope between the two endpoints is negative 1. So there's a derivative, okay, there's a x value that you could put in that's in between negative 1 and 1 that would give you a slope of negative 1. And where it is that x equals negative 1/3. And that's what this is telling us. All right. So for this next one, okay, we want to look at what's f of x is equal to the absolute value of sine of x, okay? So let's take a look. What does y equals sine x look like, the graph of it? Okay, because we have to determine, is it continuous and is it differentiable in between negative 1 and 1, okay? So sine x looks something like this, okay? So it's doing, you know, coming up like this. Okay, so right around negative 1 to 1, it looks like this right in here. Okay, so when I take the absolute value, remember what the absolute value does is it takes all the positive values and stays the same, but all the negative outputs makes them positive. So this part right here is going to get flipped up. So the graph of y equals the absolute value of sine of x is now going to look something like this. It's going to come down like this and up like this. And what do we know about that right there? Okay, is it's not going to be differentiable. Okay, at x equals 0, it's not differentiable. Okay, it's also, but it is continuous, right? So we could say f of x is continuous, because that's the very first part. It is continuous on -1 to 1, but f of x is not differentiable at x equals 0. Okay, and it needs to be. Okay, so that what that means is, because it didn't meet the conditions to use the mean value theorem, okay, we can't apply the mean value theorem. Okay, so it's important that you know when you can apply it and when you can't. So it has to be continuous on the closed interval and differentiable on the open interval. Okay, so let's take a look at this next one. Okay, so this next one is f of x is equal to the square root of x squared. Okay, so the square root of x squared we've seen a lot of times. That's really the absolute value of x. So this is f of x is equal to the absolute value of x plus 1. Okay, and so that is just the absolute value function shifted up 1. So that's going to look like this. Okay, so what does that mean? Well, it's continuous, right? So we could say f of x is continuous on the closed interval -1 to 1, but because it has this corner right here, okay, f of x is not differentiable on, and we could say it like this, -1 to 1. I'm writing this a different way so you see different ways of writing it, okay? So since it's not differentiable because there's a corner here at x equals 0, okay, we can't apply the MVT. So if it's not continuous and also if it's not differentiable, we can't use the MVT, okay? Last problem here, okay? So this is a piecewise function. So f of x is equal to x cubed plus 3 for x is less than 0, x squared plus 1 for an x is greater than or equals 0 on -1 to 1, and 0's in between here, right? So this is a cubic, it's continuous, quadratic, continuous, but where it changes pieces is it continuous, okay? So if you put 0 in here, we get 3 out. If you put 0 in here, we get 1 out, okay? So the left and right limits at x equals 0, they're not going to be the same value. So we have a jump discontinuity at x equals 0, okay? So this one has a jump discontinuity at x equals 0, okay? So what does that tell us? That tells us f of x is not continuous on the closed interval -1 to 1, okay? And that alone says we can't use the MVT, right? But because it's not continuous, it's also not differentiable. So I'm going to keep going, okay? So and not differentiable on the open interval -1 to 1. Okay, so what does that mean? That means we can't use or apply the MVT. All right. Let's go to the next problem. So a CHP officer spots you on Freeway 99 in Selma, and his radar clocks you at 60 miles per hour. Okay, so what's the speed limit on 99 here? It's 70 miles per hour, right? So the officer radios ahead to a second CHP officer 50 miles north of Selma on 99 and gives him a description of your car. Okay, 30 minutes later, the second officer radar clocks you at 60 miles per hour. The second officer turns his lights on, pulls you over, and he gives you a ticket for speeding. Why? All right. And I'm going to tell you, this is actually how on turnpikes, okay, or paid sections of road, they can tell if you sped without a police officer being present, okay? And you can get a ticket for it, all right? So I'm going to explain how the heck could this have happened, right? How did the second officer know to pull you over? He only clocked you at 60 miles per hour, all right? And 50 miles north of Selma, the speed limit is 70 miles per hour, okay? So you're going under the speed limit, right? What the heck is these police officers' problems, right? All right, so here we go. This is what it is, okay? We have to find the average rate of change, okay? So what the heck is the average rate of change? Well, that's the change in distance over the change in time. Well, we know we went 50 miles, okay? So we're gonna find the average, basically the average velocity is what we're doing, okay? So average rate of change. Okay, so we know we went 50 miles. And 30 minutes later, okay, so it helps us to understand the speed limits are posted not in miles per minute, but miles per hour. So 30 minutes is really a half hour, right? So we're going to divide this by the change in time, which is a half hour. And we have a complex fraction, right? So I need to multiply the top and bottom by 2. So that gives me an average rate of change of 100 miles per hour. Okay, so his average rate of change was 100 miles per hour. Well, heck, in Selma, he was going 60, and he was going 60 here, right? But what this tells us is that there has to be a point in time in those 30 minutes in which he had to have hit the 100 miles per hour, which means he broke the speed limit, right? So he's got to get a ticket. Okay, so because the average rate of change is this, there must be an instantaneous rate of change, right? So f prime of c that must equal 100 miles per hour. Okay, and so he, at some point in this time, he had to have gone 100 miles per hour. Okay, so we would say by, this is not as formal as the other ones, okay? By the MVT, the driver had to have driven 100 miles per hour at some point in that 30-minute time interval, okay? So between when the first officer clocked him and the second officer clocked him. I'm thinking of other ways to say this right now. Okay, so you could also say, all right, in that 30-minute time interval, okay, the driver had to have driven 100 miles per hour by the mean value theorem. Okay, all right, let's do the next one. The mean value theorem is asked a lot of times on the AP exam, and most often it's asked in the free response portion, okay? So they're actually really easy problems, okay, to write up because there's not much to it, all right? Okay, so here's a table of values. We have f of x, f prime of x, g of x, g prime of x, okay? So this is a table problem, okay? And this is part B from the 2014 FRQ number 5. So the twice differentiable functions f and g are defined for all real numbers x. Values of f, f prime, g prime for various values of x are given in the table above. Explain why there must be a c for -1 less than c less than 1 such that f double prime of c is equal to 0. So one of the key words here is the twice differentiable functions, okay? So f, since we're talking about f double prime, f is twice differentiable, okay? Okay, so if it's twice differentiable, differentiability, remember, implies continuous. So by just saying this, we have the continuous piece and the differentiability piece, okay? All right, so now this is now the second derivative is the derivative of the first derivative, okay? I know that's really kind of weird, okay? But since we're talking about f double prime, what we're referring to, the function we're referring to is f prime, okay? So not f. So f prime of x is continuous on, and since we're talking about this, it's continuous on -1 to 1 and differentiable on -1 to 1, the open interval. Okay, and so then period, and then by the mean value theorem, MVT, there must be a C in this interval, -1 to 1, okay, such that, and then here we can work it out, okay, f prime of C would sorry, not f prime of C, f double prime of C, because that's what we're working on, right? F double prime of C is equal to f prime of 1 minus f prime of -1 over 1 minus -1. Because again, remember, the second derivative is the first derivative of f prime, okay? All right, so what's f prime of 1? So we look at our table, f prime of 1 is 0, okay? So this is equal to 0. F prime of -1, so f prime of -1, that would be also 0. So 0 minus 0 over 1 plus 1, that'd be 2. So that'd be 0 over 2, which would be 0. So that means f double prime of C is equal to 0. So okay, so there has to be, this has to happen, okay? And that's the write-up, okay? A big deal is to write up the hypothesis, which is the if part of the condition that needs to be met, and finding this average rate of change and showing that it's equal to the derivative, okay? So this is the derivative of f prime, right? Okay? All right, so let's do another one of these. So once again, okay, we're given, this is the 2013 FRQ and it's part B again, okay? We're given the function C of t, table of values. A lot of times these are given on table problems, okay? And we want to show that there's a derivative that's equal to 2, and we're talking about between 2 and 4, okay? So hot water is dripped through a coffee maker, filling a large cup of coffee. The amount of coffee in the cup at time t from 0 to 6 is given by a differentiable function C. So there you go. We know it's differentiable. What does that mean? It's continuous. So we have both, okay? Where t is measured in minutes, select the values of C of t is measured in ounces, are given in the table above. Is there a time t with 2 less than or equal to t less than or equal to 4 at which C prime of t is equal to 2? Okay, so I would just go through this. Okay, let's first find, okay, what is the average rate of change between 2 and 4? Okay, so C of 4 minus C of 2 over 4 minus 2. So I'm doing this a little bit differently than I did the last problem, okay? So C of 4 is 12.8 minus C of 2, which is 8.8. Okay, and so this would be 2. And so 12.8 minus 8.8 is 4 over 2. So this is 2. A lot of times the math is really simple, okay? So this is equal to 2. All right, so that's the average rate, right? Okay, so because the average rate is 2, then we know, because it's continuous and differentiable, that there must be a instantaneous rate of change at some value of t in which it's equal to 2, okay? So we would say C of t is continuous on the closed interval 2 to 4. And it's also differentiable on the closed, but we need it to state that it's on the open, okay? So C of t is continuous on the closed interval 2 to 4 and differentiable on the open interval 2 to 4, period. So we've stated the conditions that need to be met to use this theorem, okay? So now we can use it by the MVT, comma, there must be in this case, it'd be t. There must be a t in 2 to 4 or on, okay, such that C prime of t would equal 2, okay? Because we showed that the average rate of change is 2, so there has to be a derivative that's also 2, okay? Just another way of doing it. Now, if you had not written this in such that, and then you put C prime of t is equal to C of 4 minus C of 2 over 4 minus 2, and you worked it out and got that to be 2 like we did up here, that'd be fine too, okay? A lot of times they'll give you a point for just working this out. All right, let's do one more of these. Okay, so the continuous function f is defined on this interval -4 less than or equal to x less than or equal to 3. The graph of f consists of 2 quarter circles, so quarter circle right here, another quarter circle right here, and one line segment, that's this one, okay? As shown in the figure above, and let g of x equal this. I know you don't know what this symbol is. This is just a root of one of the free response questions, and this is just one portion, okay? So here, this is what it's asking. Find the average rate of change of f on the interval -4 less than or equal to x less than or equal to 3. So just when it asks you to do something in one sentence, just do it, okay? Don't worry about anything else. Just answer that one question. Find the average rate of change, because they're going to give you points for just doing that, okay? So to find the average rate of change, that's the slope between the endpoints here. So that would simply be f of 3 minus f of -4 over 3 minus -4. So f of 3, since this is the graph of f of 3 has to be -3. So this would be -3 minus, and f of -4, well, that's -1. So -3 minus -1 over 3, this becomes 3 plus 4, which is 7. And this would be -3 plus 1, which would give you -2 over 7. So we found the average rate of change, okay? There is no point C between -4 and 3, for which f prime of C is equal to the average rate of change. Explain why this statement does not contradict the mean value theorem, okay? So here's why. Okay, so this is saying basically we can't use the mean value theorem, right? Okay, so why is that? It's saying the continuous function f, and we can see f is continuous, right? But what the problem is it's not differentiable, right? There's a place right here at x equals at -3, it's not differentiable. It's also not differentiable at x equals 0, because that's a corner right there. This one's a vertical tangent, and this one is a corner. So there's actually 2 places that cause this to happen, okay? So, all right, so we could say, all right, so f of x is continuous on the closed interval -4 to 3, but is not differentiable on the open interval -4 to 3. F is not differentiable at x equals -3 and x equals 0. We cannot, or we can't apply the mean value theorem. Therefore, the statement does not contradict the mean value theorem. Okay, so we're done with the mean value theorem, okay? So let me tell you this. This is on your final, okay? Definitely, it's on your final, and it's in the free response portion, okay? So make sure you know this, okay? Because it's easy points, all right? You just got to verify that either you can use the mean value theorem or you can't use the mean value theorem. And it's very similar to these 3 questions that I just asked you, okay? All right, so I'm telling you, this question's on your final, all right? Okay, not this exact one similar to it, okay? All right, okay. You guys have a good day.